file. Could you just
Ah.
this? So this in your pocket,
This in my pocket.
and this you attach it to the other
Where I
pocket.
can.
Yeah.
Okay. So it works? Yes, it does.
Yes.
Okay. So today we'd like to present some work with my PhD advisors, so Francis Bach and Pierre Gaillard, and it will be about function interpolation. So what do I mean by function interpolation? So I have a function, define an asset, say 0, 1, and I observe it at IID randomly sampled points on 0, 1. Okay, so they are random points, and observe a value. How well can I estimate the function from these values? So it depends. It depends on the regularity, the smoothness of the function. We will measure the smoothness with Sobolev space, HS. So here there is a power, and this indicates, roughly speaking, how many times you can differentiate your function. Except that this doesn't have to be an integer. And so, in fact, you can define rigorously these spaces by looking at the Fourier transform, and looking how fast it decays at infinity. Okay, but still we have a rough notion of regularity of functions, and depending on this regularity, it will tell us how much we can expect the function to be close to the closest points. Okay. So this is the problem, and now I want to look at one particular algorithm to do this, which is stochastic gradient descent. So how does stochastic gradient descent work here? Because it's a bit different from the usual way to use it. Well, you start from the guess 0, the function always equal to 0, and then it's an online algorithm. So it takes observation one by one. So you start from observation U1. You observe a value, and then you change the function so that it fits at this point. So you take a kernel. You can choose the Gaussian kernel of Laurent yesterday. And then you update your function using the Gaussian kernel. Okay? And then you take the next sample, and then so you observe this one, and you update your function, and now it does something like this, and so on, and so on. Okay. How fast does it approximate of a function? Now it depends on two things. It depends still on the smoothness of the function, but it depends on the smoothness of the kernel. And this is what I want to detail. Okay? But I'm not only interested in 0, 1, the set 0, 1 here. Because I want to have a discussion that can incorporate typical cases in machine learning. So I want to have at least 0, 1 to the power d, but in fact I want to have any set u here. But if I put any set u, something that has no structure at all, what does it mean to be smooth? It's not clear. Okay, it was not a joke. It's really not clear. But in fact, there are definitions of smoothness in kernel spaces. So that if you fix the kernel on your set U, you can define what it means to be smooth for this kernel space. And this is something that will not only appear for this problem, but in all the analysis of kernel methods, it always appears. So this is something that can be interesting for you in general. Okay? Okay, so now maybe I should start presenting the actual talk. And so I need to fix notation. Okay. So I want to do a supervised, statistical supervised learning. So I want to predict an output from an input. And the input lives in my set without any structure, Q. And I have access to ID samples, U1, Y1, to UN, YN. Okay? I want to find a function that minimizes the quadratic risk. Okay. And so, just like Florent yesterday, I'm going to start with linear regression. So linear regression is not such a good idea usually in input space, but maybe there is some transformation of the input that I can design myself, which works fine. So if I restrict myself to the functions of the form theta dot phi of u for phi wisely chosen, then I can approximate the minimizer of the risk. It's reasonable. When you do this, it's really important to notice that by choosing phi, you choose a big a priori on your problem. You expect that functions of this form are good to do prediction. If you're wrong, then you will have an approximation error, meaning that you cannot do better than the best of this function. So once you realize this, you're tempted to add more and more features here to have more and more expressive power. But then the computational costs grow because you have to compute more and more features. So here there was a trick that was invented, which is the kernel trick. So you've heard about it yesterday, but maybe a little reminder is a good idea. If you do linear regression or ridge regression, you don't need to compute these guys. You only need to compute dot products between features. And what we call dot products between features are in fact kernels, positive definite kernels. So you take functions of two entries, and there are assumptions that guarantee you that there exists a lifted space, a feature space, and a feature map, so that this function is in fact a dot product after the transformation. Okay? And now, to run your algorithms, you only use this function. And typically, for instance, with the Gaussian kernel of yesterday, these spaces are infinite dimensional. So it would not been possible to compute this. Any questions so far? Yep. They are what? Equally spaced is not a notion that will generalize to any set U. There are studies for equally spaced in this particular case, and it's not important, but for the generalization and for my analysis, it's fundamental that it works this way. Any other questions? Okay, great. So as I said, because this is infinite dimensional, you have a lot more expressive power. And in fact, the set of functions linear in feature space is dense in L2. So you will approximate, not always, but for many kernels, it's dense in L2. For the Gaussian kernel, it's dense in L2. Okay? So you will be able to approximate any function. Okay, let's give an example. So back to the simple case, 0, 1 or 0, 1 to the power d, but it doesn't change much. So I will see this as a torus, so it means periodic boundary conditions. And I will choose a kernel that depends, in fact, only on the difference between u and u prime. And the function t of u and u minus u prime, I define it by its Fourier transform. Okay, and I want to have different decays of Fourier transform, so I introduce a parameter s, and this controls the regularity of t. Okay, so t looks like a bump function, but now I control how the width of the spike, how spiky it is. Okay, and remember that kernels are what you think of the similarity of your data. So this spike matters a lot. It means how you think that from one data point you can generalize to the others. If it's very spiky, it means you don't think you can generalize a lot. to nearby points. Okay, so it lives in a Sobolev space HS, well, almost. So it lives in HR for all r strictly smaller than s. And then if you look at all the functions that you can reach that are linear in Fisher space, it's not obvious, it's a computation you must do. You get a Sobolev space also. Okay? You know who phi is here? I didn't try. No. So the answer is no. It's dense in L2, by the way. Okay. So it sounds from a machine learning point of view that it's a bad idea to take a set dense in L2, because if you can approximate any function, then you have no a priori and then you will overfit. It's not true, because typically you will regularize. So you will restrict to thetas that have a small norm. And so finally you will end up being in this set, not near any functions. You will end up being with functions with a small Sobolev norm. Okay? This is the a priori of your kernel. So again, the choice of a kernel indicates a strong prior on the structure of your problem. And if you take any kernel, among the functions in H, there is a continuum of regularities that you can have. There are functions that are more or less regular. Okay? So now I'm talking about functions. So remember there are theta and f of theta, and I tend to mix the two. Okay? So now you have to be a bit more agile in your brain. But okay, there are the functions that are represented by a representer in H, and there are functions that are in more and more smaller spaces. And these are functions more and more regular. And it turns out that the right notion is to look at sigma, the covariance of the features. So expectation of phi of u, phi of u transpose, it would be a matrix if we were in finite dimension, but here it's an operator. And then the powers of sigma, the image of the power of sigma, give you a continuum of smaller and smaller spaces. Okay? The larger the exponent, the smaller the space. Okay? Now, if I take a function, say f star, which is an interesting function, the minimizer of risk, and I want to understand how regular it is in my kernel space, I take its representer. I assume that it exists here. To make things simple, that there is a representer. So my assumption is in some sense right. And then the regularity, which will be the larger exponent, such that theta star is in sigma alpha over 2 of H. This is the first very important exponent. There is a second very important exponent, which is the regularity of the features. The features also live in H, and you can wonder how regular they are. Remember, it's a random variable. But I take the exact same definition, but I add almost surely. I want phi of u to be in sigma alpha over 2 of H almost surely. So these are the two parameters, and I call them regularity of the optimum, regularity of the features. So this is the energy barrier of this talk. So if you have any questions, it's a good moment.
Yeah, I'm wondering how should I think about the alpha beta? How are they chosen? They are given, like they are any, or
So you can think of what they depend on. Alpha 2 depends only on the kernel.
No, I mean alpha and beta.
Al
Alpha 1 and alpha 2 are clear given alpha. I don't know what to think. Is it the same alpha that in the line above?
So this is the same alpha, but these are not fixed. These are variables. I'm just describing, this was just an introduction to this. And I'm just saying there is a sequence of a continuum of embedded spaces, just like Sobolev spaces. But here, they don't mean anything right now. And now I define two alpha 1, alpha 2 that are important.
I'm missing how sigma acts on H.
works on H.
I guess my question then would be on H that is a little bit for alpha half.
It's confusing. Maybe I give an example to make things like so confusing. Aha, top example. So I take back u equals 0, 1 to the power d. I have my bump function. I control how spiky it is.
That's why I was asking phi of u for this example. Do we need to see or
Yes.
covariance of it?
Yes. Phi of u doesn't usually help.
No, I understand, but we need the covariance of the theta.
I don't know. What you can compute is what are the functions corresponding to thetas in sigma alpha over 2 of h. And it turns out they are all also Sobolev spaces. And they are more and more of with a high exponent. It increases with alpha. Okay? So in that case, it happens that this notion of regularity in kernel spaces is Sobolev regularity. It doesn't have to be. It's just in this case. Okay? And then here there is scaling that depends on S, the smoothness I've chosen for this. So this is the only intuition that I have, basically.
Okay, so it's not something like very easy.
No.
It depends on what's still there.
It's a bit a technical thing that always appear in the analysis of kernel methods, I would say. But I'm not an expert. Okay. So summary of a difficult part. There is a kernel theory that extends linear regression to nonlinear situations. It corresponds to an infinite dimensional change of variables, implicitly. And thanks to the kernel trick, it remains implicit. You never have to compute things. When you choose a kernel, you make an assumption. And the kernel defines a scale of regularity that you will use to measure regularity of functions. Okay? This formalism was introduced by Camponeto and De Vito in 2007. And they used it to analyze ridge regression in kernel spaces. So they have two same exponents, and now they do ridge, so it can be done implicitly. And okay, so it's just minimizing the empirical risk plus the penalization. And here is the RKHS norm. So it's a norm of theta they represent. Okay? And they are able to say, depending on the two parameters, how you should penalize. Depending on how the things are smooth, how much you should penalize. And they give a rate of the excess risk. There's not much to see in the exponent, except that here the approximation rate is increasing in alpha 1 and alpha 2. It's a safety check. The more things are regular, the faster you go. And they also proved that this rate was optimal. What does it mean? If you take the class of problems that satisfy these two, that have these two exponents, you cannot make a method that goes faster than this in the worst case. Okay? So, in some sense, this is great. Ridge regression is great, and you understand very well what happens, how you should penalize. But Florent told you the kernel matrix cannot be computed, so you cannot run ridge regression. So you need to turn to something else, and something else can be online methods. You don't use the dataset all at once. You just take a pass over the dataset. Okay, and the simplest of all online methods is stochastic gradient descent. It can also be kernelized. And it was analyzed by many people, and the take-home message is that you can also achieve optimal rates.
This is Pierre Paris?
I don't know. I don't know him actually. You can reach optimal rates, the same optimal rates, if you use some tricks, including decreasing step sizes, averaging, and of course you have to regularize. Okay.
Can I ask
I'm trying to avoid this. Okay. Okay, two people. I was going to refuse, but now I have to accept. What you want to do? Okay, can we do it at the when I show the equation for LGD? Okay. However, okay, if you talk to people that that actually do machine learning with real data, and we're lucky at Senior because we have this. And well, first you're disappointed because they don't use command methods; they use neural networks. But still, if you force them to use command methods, they will not use these tricks. So they will not decrease step sizes, or very little, let's say, compared to what the theory says. They will definitely not average, and they will regularize quite little compared to the prediction.
Average what?
Hmm?
They would not average what?
Average iterates. So the theory says that you should, instead of taking theta n and computing the risk of theta n, you're better off with the risk of theta n bar, which is the average of all the previous iterates. Okay, but it's people don't do this in practice, or maybe over a batch of 10 sample, 10 last iterates, but that's not good. Okay. Can we explain why, in some situation, plain vanilla fixed step size HGD works well? So we don't want to use any of those tricks. Okay. Here's the equation for stochastic gradient descent, now derived for real. So you have your risk, and then you compute the gradient, and you say, oh, okay, this is an expectation. Every time I have a sample, it means that I have an estimator of the expectation. And I use this estimator to have an approximate gradient, and I go down the approximate gradient.
But now theta is in infinite dimension.
But now theta is in infinite dimension. So remember, this is not done explicitly. So now I get to Lenka's question, how is it done implicitly? So here you see that you have a dot product with phi of u. So this you want to make to kernelize. So this, in fact, what you will do is use the representer theorem of yesterday. You will use that theta n is a linear combination from k equal 1 to n of alpha k phi of uk. And instead of storing theta n, you're going to store the uk alpha k. You're going to store the linear combination. Okay? Now, if you need to compute, so now this is only the computation of a new coefficient, right? In front of phi of un. How do you compute it? Well, the only thing you need to compute is this dot product, and then theta n minus 1 dot phi of un. Okay, oh, you can expand here. It's a sum of over k of phi of uk phi of un with coefficients alpha k. So they also depend on n. If I was, they don't depend on n. Actually, and then this is the kernel. Okay, and yes, does that clarify the situation? Cool. Okay, now I'm going to make an assumption. It's the noiseless model. I'm going to assume, you can maybe call that a teacher-student scenario, but I'm not so sure. You assume that there exists a deterministic relation between y and u. So you can, there's a function that given u gives you y, unless you're so it means you can achieve zero risk. And in some machine learning situation, this is realistic. If you think of a cat versus dog problem, for instance, So you have images of cat and dogs, and you want to say if it's a cat or a dog. For typical images, there is no ambiguity. There exists a function that will tell you the truth. And humans have a good approximation of this function, let's say. The problem is that this function is very complicated. So what you want to understand is how the fact that this function is very complicated makes the learning process difficult. But the difficulty doesn't come from additive noise. It doesn't come from the fact that there is ambiguity after there's a noise on top of this, of f star of u. Okay? Yes.
Sorry, in the definition of the stochastic gradient descent, it looks like you're still missing all phi, right? Like at the end, you're phi nu n.
Yes, but phi of nu n, so this will add the new, this is up plus alpha n phi of nu n. And you're not keeping in memory phi of nu n because you're not computing it. You're keeping in memory un and the coefficient in front. And the coefficient in front is what you're computing over there. Yes?
To clarify, do you also assume that there's an theta that achieves the regularization?
Yes, because
Which is the right
yes.
big phi and
Yes, good point. Because this was an assumption I made a while ago, saying that there was a representer for f star. So now I keep this assumption. Very good point.
So this is like an online version of gradient descent because you have theta n, which depends on.
This is
The
an
mu k is the data transfer, right? K is the index of the data transfer. The input, data input. Right?
yes.
So every step of gradient, you're adding information from a new data from.
Yes. This is single pass stochastic gradient descent. I don't make several passes over the data, so I just take one sample, compute the coefficient in front, and then I'm done, and I take a new sample, and I continue. Okay. Now is the result for this. So, covariance matrix and the two parameters, same one as before. And now I study stochastic gradient descent, the one that I've just shown you, and I don't decrease the step size. I take constant step sizes, small enough, there is a constant, it needs to be smaller than a constant. And then, first surprise, stochastic gradient descent converges. So this picture of stochastic gradient descent going down a convex landscape and then moving around the minima, it's not true. Here it really goes to minimum. Okay? Okay. Second, the rates of approximation depend only on the minimum of the two regularities. Okay, and then you can, so there are theta n and fn are random variables because they depend on the sampling of the un. But if you take the expectation, then you can tell the rate of approximation. And here it happens to be the minimum on the two regularities, and here minimum plus 1. Okay? For the risk. Here, a detail, we don't have a result on expectation of risk of Fn. We have that the minimum of all the past iterates, among them there was one that was good. Now, if you remove this and you have a result of on expectation of a risk of Fn, any rate, depending only on n, I'm interested. Okay? I don't know how to do things without the mean. Okay? So let's...
You don't have a stopping rule then?
don't really know, not really know when you want to stop.
No. No, but okay. In fact, here is single pass SGD. So you cannot. You have in practice you have a finite data set. So the stopping rule is you are at the end of your data set.
If it is single pass, shouldn't the expectation at all time be equal to
single pass in expectation, I don't see why your training error will be different from the regression error.
Yes. Well, that's why we get results on the generalization.
Yeah, but then you have a minimum, so I'm not sure to see why it's different.
Oh, it really comes from the analysis. Well, okay. Maybe, okay, I'll derive in this case what it gives. So this is the case that I've just drawn here. So you start from you have a function. Here it's of regularity 2, but you don't, r equal 2, but you don't really see it because there are kinks. And then you start from the initial guess 0. Yes?
So can I ask another question?
Yeah.
I didn't quite understand. So do you do one pass to a fixed training set, or do you do one pass until you converge? So you have as much data as you want.
Well, I mean, from the formalism, it's the same thing. You see, when I mean, I model it as an infinite sequence of samples.
Okay, so you can draw as many samples as you want.
Yes, but
at some point you will converge.
yes, but if you have a finite number of samples, which is the practice, then you have to stop at time n, and this is what I tell you of your performance at this point.
Okay.
Is that clear?
So the first part is telling us that as you iterate, you are getting closer and closer to the target.
Uh-huh.
Then why is it that there is some error should improve as you iterate? So the minimum should be the last one?
Yes. Yes, so it's easy to show that you're right. You're right, which means that I can prove that the expectation of the risk of Fn, the last iterate, is smaller than this quantity.
Yes.
Having the plus 1 is difficult.
Okay.
So you're right. My open problem is not the one that.
Okay, sorry, I got it now.
Yes, this is the part where it's hard to have the extra rates, because it's funny. It goes faster in risk than in iterates in representers. Okay. Back to my function approximation. So I have my kernel, and I see here I took the samples seem to be here. I see the value, I update, and then I continue. After 20 steps, you get this, and you wonder how fast you approximate the function. Okay, so if the function, the true one, is in HR, and the kernel is in HS, then you can tell in L2 norm how fast you will approximate. And it's the minimum over two quantities. And I agree that it's kind of hard to read, but the point is, in practice, R is fixed, the function is fixed, and you choose the kernel. Okay? And you want to maximize the rate of approximation. And here, the rate is a minimum between two quantities, and one is increasing in S, and the other is decreasing in S. So there is a trade-off here. And if you actually do the computation, the optimal smoothness is when S equal R. The two smoothness match. Was it obvious from the start? I don't know. Any questions? Just some simulations to relax. The same function with regularity 2, and then I take 3 kernels of smoothness 1, 2, and 3. And then I look in log-log scale what is the performance of the approximation in L2 of iterates. So I get the Pru curve, so it's a function of n. And then my prediction is that it's a line in log-log plot with a certain slope. So, and I see that the slope, indeed the minimum matches the slope here in the 3 cases. And indeed, it is fastest when S matches R. Okay? There's also a dependence on the dimensions. But in the trade-off, like in the optimality, it cancels out. you need to do, well, no, maybe you can do it by like this, but it happens to cancel out perfectly. So the dimension doesn't appear on the optimal choice of the kernel. And so what you see is that the minimum indeed follows this slope, but it doesn't seem the case for our risk of Fn. Well, does it? It's not obvious from the simulation. I still don't know. Okay?
Notice it's when C is very large and R is equal to S, the first term is very small, and that's the minimum.
Let's see. So the optimum is reached when the two things in the minimum match. S plus d over 2 is equal to 2 minus d over s plus d over 2. Okay. I multiply by 2r equal to s plus d over 2 minus d. Yes. And now I have 2d over 2 minus d. The d cancel out. So this cancels out with this. I have 2r equal to s, r equal s.
Okay. Or the right, the R is still extended. Okay, now I get
Yes.
it. Okay, I was thinking like this.
Okay. Take home message. We introduced the noiseless assumption, which is a surprising assumption under which fixed step size stochastic gradient descent with no explicit regularization converges to the optimum. We have given the rates, and I have to say that they are non-optimal. So if you look at the statistical optimal rates for this problem on 0, 1, we know that we can do faster. So there may be smarter things to do, but still it's a good baseline. The noiseless is y equal f star of u. There is a rule giving y given u. Okay, you can achieve zero generalization. And thanks to these rates, you can show the trade-off in the choice of the kernel. And this trade-off is the trade-off between the regularity of the optimum and the regularity of the features. Okay, should I end now? How much time do I have?
Can I just like ask, like you
Yep.
see the case of the instability, right? Because if R is equal to S, then the minimum is 4 over D, correct?
R equal to, where is the best place
What
to?
is the first term?
Here? No, yeah, this one is the best one.
R is equal to S, and D very large. Or not
Yes.
very, but you have the dependence of
You divide by R, you get this. And what you see is that to have a big rate, you need R to be as large as D,
right.
which means that smoothness regularity is not the right notion to measure things in high dimensions.
Yeah, okay.
And this is not a surprise. This is why we made a big effort to make the analysis not only in Sobolev spaces, but in kernel spaces. In practice, you will use kernels that are more adapted to high dimensional problems.
I see, so kind of being in the kernel space reduces the effective dimension.
Yes, you can hope to choose kernels that, choosing these bump functions is only like you assume locally that things are the same. It's like doing Gaussian, but like using the Gaussian kernel. But it's not a smart idea in high dimension. You need to use more structure of your problem.
In the previous slide, what was the choice of the kernel that we made?
The choice of the what?
Yeah, but the choice of the kernel. What kernel did you choose in the last slide, the results that you showed?
I'm sorry.
The results that you showed in your last slide.
Yep. This one.
What kernel did you choose? Yeah.
Oh yeah. So it's this problem here, and remember the kernels that I introduced in the beginning. With the parameters that I could change. S. It was more. It was this bump function, which could be more and less flaky, and now I take 3 of them. the one for s equal 1, s equal 2, and s equal 3. It gives me 3 simulations. And I look at the matching between theory and practice. Okay. Any other questions? Am I out of time? Yeah, probably.
Well, we had a lot of questions, so if you want to take one or two more minutes, we started a bit late.
No, I have
Okay.
10 minutes extra, but maybe it's too long.
Great then.
Okay, thank you.